Hello, in this video, I'm going to introduce phase changes between solids, liquids, and gases. If you haven't already, please print out these notes, and it's good to have a written version of this and to write along as we go. Certainly you don't have to do that. I will be reading along and filling things in similar to what we do in class. So phase changes, when we're talking about the three phases, the three main phases of matter, solid, liquid, and gas. And a phase change is when we're going in between any of those phases. So these occur when energy or heat is added or removed. And these are physical, not chemical changes. We're not creating anything new. We've all heard of evaporation before. Sometimes it goes by the fancy name of vaporization. That is when liquid is being turned into a gas or a vapor. It could be happening slowly or quickly. If we think about a liquid, at a given temperature, all the little molecules in there are moving with various amounts of kinetic energy. And since the temperature is an average, some are moving faster and some are moving more slowly. If there's one particular molecule with enough kinetic energy for that molecule to escape from the liquid phase, it becomes a gas. Like I said, evaporation can occur at any temperature. But as the temperature increases, the rate of evaporation is going to increase. This is because more individual molecules will have the minimum amount of energy to escape. And you might be asking, escape what? Well, what is holding things in the liquid phase in the first place? Well, one of our favorite terms is intermolecular forces. So if you picture water with the little particles here all moving around at different energies, in order for one of these molecules at the surface to escape, it has to have enough kinetic energy to break its hydrogen bonds with the other water molecules. If I increase the temperature, there's going to be more water molecules with high energy, and more of them are going to escape or vaporize into the gas form. The number of molecules with the minimum energy needed to escape, as I mentioned before, will increase. It helps to be able to interpret these diagrams over on the right. Here we have on the y-axis number of molecules and on the x-axis energy. And if you look at this first situation, looks like a lot of the molecules have a low energy. And over on the right, it looks like a lot of the molecules are spread out over various energies. So there's an increase in the number of molecules with a high energy. So for that reason, if you want to pause and take a guess whether temperature 1 is higher or lower than temperature 2, you can pause for a second. But it turns out that temperature 1 is lower or less than temperature 2. And if you think about it, temperature 1 right here, it has a whole bunch of molecules with low energy. And as you increase the temperature, you get many more molecules which have more energy. And if you look at this pink area over here, these are ones that have enough energy to go into the next phase. So that has increased with the increase in temperature. We talked about volatility. Volatile means liquids that have weak intermolecular forces are going to go into the gas phase more readily because of those weak forces. So if we're comparing water with its hydrogen bonds and gasoline with only London dispersion forces, we would expect the gasoline, C8H18 or octane, is going to be the winner. So this is more volatile. just like hexane in our lab, because there are less intermolecular forces, or weaker intermolecular forces, LDFs versus hydrogen bond. Evaporation is a cooling process, and anytime you guys have gone for a run and started sweating, so when that sweat evaporates, it's actually taking heat away from your body, and the evaporation process is allowing you to get cooler. So as the water molecules on the skin evaporate, the high kinetic energy molecules turn into gas, leaving behind the cooler or the low kinetic energy molecules. Let's talk about vapor pressure for a second. Again, talking about a liquid. As gas molecules are evaporating, those molecules are going to bounce around on, well, the surface, or you could put a balloon over there. So when a liquid evaporates, its gas molecules exert a pressure over the liquid. So they're going to bounce off everything, the inner walls of this beaker. They're going to bounce back on the surface of the liquid. And then, of course, if there's a cover in it, it'll bounce off those as well. Equilibrium vapor pressure means, well, equilibrium just means the rate in one direction is equal to the rate in another direction, or the reverse. So equilibrium vapor pressure is the point at which the rate of evaporation and the rate of condensation are equal. So if you imagine this liquid where a bunch of liquid molecules are evaporating, and at the same time a bunch of gas molecules are condensing, you would get a dynamic equilibrium where these are happening at the same rate, and you would not have a change in your volume at all. When I increase temperature, though, I'm going to get more evaporation, and I will get an increase in the vapor pressure. So anytime you're in a jacuzzi, you see this, where not just the bubbles in the jacuzzi, but at a high temperature, you can see the steam effectively leaving the jacuzzi. Or if you're getting close to boiling your noodles or your hot chocolate, this will evaporate faster, and those gas particles will exert more of a pressure. Super important definition here is boiling point. Once you get to higher and higher temperatures, you'll see that you get higher and higher vapor pressure. So here at 25, we get a relatively small water vapor pressure. But if I get up to 80 C, this is getting to be a much higher pressure. And when I get up to 100 degrees Celsius, I actually get a vapor pressure that is equal to our standard boiling temperature, or our standard atmospheric pressure. So boiling point is when the vapor pressure, so the pressure that's coming off a liquid, is equal to the pressure of the atmosphere pushing down. And what we see are a whole bunch of bubbles. So when we get to this really unique point, the boiling point, like 100 degrees Celsius for water, is when we get this temperature when the vapor pressure going up and the atmospheric pressure pushing down are equal. So it's important just to memorize that, but also to understand what is going on in that process. So those liquid to gas phase change is happening quite rapidly, but at the same time you have pressure pushing down, so you get these competing things. Boiling is also a cooling process, and if you think about what's going on when you're boiling your water, you're adding heat under your pan, and at the same time the temperature is not going up. So what is allowing this boiling water to stay at the same temperature? Well, it must be because while it's getting heat from the fire below, it's also cooling off by evaporating a bunch of water molecules. So as a substance boils, the high kinetic energy molecules escape, and it leaves behind the cooler, or the low kinetic energy molecules. If there's a heat source, it will keep the temperature at it'll keep it at a boil. It'll keep it at its boiling temperature. The normal boiling point of a liquid is the boiling point at standard pressure, which we should all remember is 1 atmosphere or 760 millimeters of mercury. 760. And it kind of helps to look at these diagrams because the external pressure at sea level means the pressure is pushing down at normal atmospheric pressure. And if I get the temperature up here to 100 degrees Celsius, it will push up, or the vapor coming off it will push up at the same pressure and we'll get boiling. So at regular atmospheric pressure or normal boiling point, we get 100 degrees Celsius. If we're somewhere like Death Valley where there's more pressure because you're at a lower elevation, you're going to have to heat up this water more because the air pressure is higher. If the pressure is at 800 millimeters of mercury, then we have to heat it up to a higher temperature. And in this case, 101 degrees Celsius is what's required in order to boil water. So you actually have to get a higher temperature to overcome the higher atmospheric pressure. If we're at the top of Mount Everest, there's very little air up there. So just a little bit of air pressure, which means we aren't going to heat up our liquids as much in order to get this. So at 71 degrees Celsius is the highest temperature you can get water. So your boiling water at the top of Everest is much cooler than your boiling water at sea level or at Death Valley. So if you want to pause each of these as we go through, or just a quick pause, does it take more time or less time to hard boil an egg on the top of Mount Everest or at sea level? So pause, think about it for a second, answer it, and then come back. It's actually going to take more time. And this can be a little confusing because you're like, well, it only has to get to 71 degrees. So isn't it going to boil quicker? That's true. It will boil more easily, but it'll also boil at a lower temperature. So it's the high temperature that cooks the egg, not the act of boiling. So at 71 degrees, it's not as hot, so it'll be a lower temperature. So that means you're going to need a longer cook time. So if I'm boiling water on the stove and I turn up the flame to make it boil more aggressively, will I cook spaghetti faster? And based on what we said earlier, boiling temperature at sea level is 100 degrees Celsius. So if I turn the fire up higher underneath, it might boil faster, but it's going to stay at 100 degrees Celsius. So we would actually get the same cook time. It'll just boil more vigorously. Well, what if I put a lid on a pan? Will that cause something to cook faster? And the answer is yes. If I put a pan on it, what's going to happen is it's going to slightly increase the pressure inside the pan, because those gas molecules that normally would be escaping are going to be pushing around above the liquid. So a higher pressure, just like when we look up here in the Death Valley or Part B scenario, if I have a higher pressure, that means it's going to boil at a higher temperature. So if I have a higher pressure, I will get a slight increase in my boiling point. So that means it'll be hotter. And stuff will cook faster. A pressure cooker just takes that and exaggerates it. So if I seal the lid over something, I will get a much, much higher pressure, which means I'll get a much higher boiling point, and I'll have a lot hotter water and steam to cook my stuff. So I'll have a higher temperature cooking environment. Okay, a couple more things. Critical temperature and pressure. So For condensation, real quick definition, this is the opposite of vaporization. So where vaporization is turning a liquid into a vapor, condensation is turning a vapor into a liquid. So one way to cause something to liquefy is to lower the temperature. And that decreases the kinetic energy of the molecules in the gas phase. And the other way to liquefy something is to raise the pressure on the gas. This is how many gases are liquefied. If you see any liquid carbon dioxide trucks driving around, or if you have liquid propane in your barbecue, the reason is those are pressurized, and once you let them out into the normal atmosphere, they become gases. So when you increase the pressure, as the distance between molecules decrease, the strength of the intermolecular forces will increase. So things get closer together and they're going to start interacting more, and that will cause them to liquefy. All right, critical temperature. Above the critical temperature, a gas cannot be liquefied. So this says this is the maximum temperature at which a substance can exist as a gas. The maximum as a liquid, pardon me. So above the critical temperature, it cannot exist as a liquid. So molecules have too much kinetic energy, so that the intermolecular forces are no longer strong enough to liquefy them. As the strength of the intermolecular forces increase, the critical temperature also increases. Critical pressure is the minimum pressure that must be applied to bring about a phase change. At the critical temperature. So a couple last things. Liquid solid equilibrium, we call it freezing, is the transformation of a liquid to a solid. The reverse is melting, or if you want to use a fancy term, fusion. The melting point or freezing point of a substance is the temperature at which solid and liquid phases coexist at equilibrium. So that's like your icy beverage where you have both solid and liquid at the same time. So if you have ice water or iced tea in front of you, the temperature is going to be really close to 0 degrees Celsius because you have both phases together. And most of you guys have heard of sublimation. That is when you transform a solid into a gas. This is what happens with dry ice or iodine. The reverse of this is called deposition. One example of this is frost. So if you get frost that shows up on your windshield, that is when you have gas in the atmosphere, water vapor in the atmosphere that turns directly into a solid. That's it for now, and we'll continue on later.